So the first thing we want to talk about in this section is the average rate of change. So a key part of this is our rate of change is our keyword for slope. And we actually know what that is. So we have our nice formula for slope, right? So our slope m is y2 minus y1 all over x2 minus x1. But now we've got this extra descriptor, average. The idea is we want to generalize the idea of slope to other types of functions. So if I had a function f that looked like this, and I had some associated inputs a and b, I would then have some associated outputs with those, f of a and f of b. Well, that would give me the ordered pairs a comma f of a and the ordered pairs b comma f of b. The idea of the average rate of change is if I connect these 2 points with a secant line, I know how to find the slope of this line. So the slope of the secant line that contains a f of a and b f of b is the average rate of change of f on the interval AB. So when you hear average rate of change, what you should really just be thinking of is the slope formula. So we're finding the slope between 2 points on a graph. The function f does not necessarily have to be a line, because if we can find 2 points on f, we can connect 2 points to make a line and then find its slope. So then our average rate of change is given by the formula f of b minus f of a all over b minus a. And that's really just the slope formula. So when you hear average rate of change, we're really just talking about the slope. So no matter what the function looks like, you can find 2 points on that function, and you can find the slope that contains those 2 points. All right, so let's go ahead and take a look at example number 1. So example 1 says, in 1998, the average price of a barrel of oil was $11.91. By 2013, the average price of a barrel of oil was $91.17. Find the average rate of change in the price of a barrel of oil from 1998 to 2013. So to find the average rate of change, what do we need? Well, according to our picture, we need 2 points, inputs and outputs that go together. So our ordered pairs are going to be in 1998. So if I input the year 1998, my output is $11.91. And if I input the year 2013, the corresponding output is $91.17. So then our average rate of change is going to be the slope between those 2 points. So 91.17 minus 11.91 all over 2013 minus 1998. So putting all that into our calculator, we get 91.17 minus 11.91 over 2013, take away 1998. And rounding to the nearest penny, it would appear that I have a typo. It should be 1191, so let's fix that. I only have 191 in there. So 11.91. All right, now it's correct. Rounding to the nearest penny, we get $5.28. So that would be our average rate of change per year. So in the context of this problem, what that represents is that on average, you would have to change by $5.28 per year to have the price of oil change from $11.91 to $91.17 in the course of 15 years. And then that's dollars per year. All right. Well, let's take a look at our next example. Example number 2 says find the average rate of change, but instead of being given discrete data points to find the average rate of change, this time we're actually given a function. So it says find the average rate of change on the interval 1, 3. So remember, each of these are our inputs. So that's my A, and that's my B. And the formula is f of B minus f of A all over B minus A. So in this case, it would be 3 squared over 4 minus 3 minus our A, so 1 squared over 4 minus 1, all over B minus A. And then we would need to simplify that down and see what we get. There is an easier way to use our graphing device to do this. So if we just put our function into our y equals, we can go alpha y equals to get our fraction. We go x squared over 4, and then we go take away x. So now that we have that, we can actually just make our fraction, and we type this in. So we have alpha trace, we select y1, so y of 3 minus alpha trace y of 1 all over 3 minus 1. And our calculator gives us that the average rate of change on 3 is 0. If you were to type all of this into your calculator right here, indeed you would end up getting the number 0. It's just that makes it a lot messier to have to type all of that in, where if you enter the function once and use your alpha trace, it will do that for you. So this one gives us 0. And now when we have to do another one, if they're numeric, we can just do the same thing again. In fact, you just type it in, but this time my A is 2 and my B is 8. So alpha trace y of 8 minus alpha trace y of 2 all over 8 minus 2. Hit enter. And this time we get that our average rate of change this time is going to be 3/2. The last one involves a variable when we do this, so we will be unable to just type it directly into our calculator. The last one wants us to calculate, well, what is the average rate of change on the interval 0, A? Well, that would be f of A minus f of 0 all over A minus 0. Well, f of A would be A squared over 4 minus A minus 0 squared over 4 minus 0, all divided by a minus 0. So then that would give us a squared over 4 minus a. All of those are 0, and a minus 0 is a. So we could get a common denominator. Simplify this up by building our fractions by multiplying the top and the bottom by 4. And we get a squared minus 4 over 4 divided by a. And we can make a fraction over 1. So multiplying by the reciprocal of the denominator gives us a squared minus 4 over 4 times 1 over a, giving us a squared minus 4 all over 4a. And that would be our average rate of change on the interval 0, comma a for every value of a. All right, so our average rate of change is just the slope of the secant lines through the points x equals negative 1 and x equals 3. So it's f of 3 minus f of negative 1 all over 3 minus a minus 1. So that's going to be 3 cubed minus 8 take away negative 1 cubed minus 8 all over our 3 minus a minus 1 is 3 plus 1. So 3 squared is 27. 27 take away 8 is going to give us 19. Minus negative 1 cubed is negative 1 take away 8 is negative 9. All over 4. 19 take away a negative 9. We're going to once again get another plus plus, which gives us 28 over 4, which reduces to 14 over 2. You can also just do it directly on your calculator by putting in our x cubed take away 8, and then we would have our fraction y of 3, so y of 3 take away y of negative 1 all over 3 minus negative 1. And yes, 14 over 2, wow. Or, yeah, apparently I need to have another coffee this morning. There we go. 14 over 2 does indeed reduce to 7, and our calculator agrees. All right. So now we want to talk about increasing, decreasing, and constant. So a function is increasing on the interval AB if for x comma y in the interval a comma b and x is less than y, then f of x is less than f of y. So So that's our formal definition of increasing. So it says if you take any 2 points in the interval a comma b, then if x is less than y, then f of x has to be less than f of y. And that's what it means to be increasing. So in terms of a picture, you have your interval a comma b, and you take 2 points x and y, and it says if x is less than y, so x would be to the left of y, then f of x has to be less than f of y. So that would mean that f of x is lower than the value f of y. So we don't know how the function looks as it goes from x to y, but it does indicate that it has to be going up, or it increases as we move from left to right. So the above is a very technical definition of the idea that a function is increasing if, as you move from left to right, it goes up. We have similar definitions for decreasing. So decreasing is almost identical So if we have x, y in our interval AB and x is less than y, if the function is decreasing, then f of x is greater than f of y. So that would mean as we move from left to right, our function is going down. All right, so then this would also indicate that it's moving down as we move from left to right. All right. So let's take a look at our first example. So from the graph of the function states the intervals on which the function is increasing, decreasing, or constant. So let's start with increasing. So that means anywhere it's increasing is where it's going up as we move from left to right. So our function is increasing here and here. So it's going to increase from -7 to -1. And it's also going to increase from, got a little out of control with my highlighter there, from 4 to 6. We do something similar with decreasing, which we decided that's where our graph is going down as we move from left to right. So that's here and here. We're going to have our decreasing, and that's from -1 to 4, or from 6 to 8. And then our last part is constant, and that's going to be right here. And that's when the graph neither moves up or down. And on this graph, that's going to be from -∞ to -7. All right. Now, your guys' turn. So go ahead and find the intervals of increasing, decreasing, and constant. So for increasing, that's when our graph moves up as we go from left to right. That's going to be this part right here. which is going to be this interval from here to here. So we're going to be increasing from -1 to -3, or from -1 to +3, not -3. And then we're going to have our decreasing, and that's where our graph is moving down as we go from left to right. So then on our graph, that would be these values. So we're going to be decreasing, and it's from -8 to -6, and also from 3 to 7. And our last one is, oops, I missed an increasing, didn't I? This little bit right here. Increasing. So need to add that right over here. So from -6 to -5, and from -1 to 3. So I'd missed this little bit of increasing, and when I came back to get the constant, I noticed it. So then we're constant here, which means we're constant here. And that's going to be from -5 to -1. And that gives us our intervals of increasing, our intervals of decreasing, and where our graph is constant. All right. So now, a couple more definitions. So the first one is for a local maximum. So the point C comma f of c is a local maximum if there exists an open interval AB such that for all x in the interval AB, f of x is less than f of c. So let's talk about what that definition means in terms of a picture. So imagine you have a graph of something that looks like this. And we're looking at the point right here, C. Our definition says if there exists any open interval a comma b, doesn't matter how big it is, in fact it can be infinitesimally small, such that for every x in that interval, f of x is less than f of c, then it's a local maximum. It doesn't matter that over here there could be another value that actually is larger, has a larger output than that one. So the idea of a local maximum is that as long as there exists some open interval around that point where it is larger than every value in that interval, for every output in that interval, then it's considered a local maximum. As hinted at by this diagram, a graph can have multiple local maximums. So in this picture, both of these are local maxes. So a graph can have more than one. In fact, it can have an infinite number of local maximums and local minimums. An easier way to help realize what's happening here is to note at a local max, the graph always changes from increasing to decreasing. So you notice at each of those local maximums it was going up. It turned around and started to go back down. When it changed from increasing to decreasing, we had a local maximum. Using the same idea, we get exactly the same idea for local mins. And you'll see, if we look at this point right here, this would be a local min. And at a local min, it's going to change from decreasing to increasing. So it has to change from going down to going back up. So at a local min, the graph changes from decreasing to increasing. All right, so armed with those two pieces of knowledge, we are now ready to do example 4, which conveniently, it's the same picture that we used in the previous problem. So the previous graph actually encodes all of the information we needed. So we're going to have a local maximum anywhere my graph changes from increasing to decreasing. So this point right here, I go from increasing to decreasing, and here I go from increasing to decreasing. So both of these are going to be local maxes. And my graph right here is going to have a local min as it changes from decreasing to increasing. So we have a local max at -1, 6, and 6, 5. And we're going to have a local min, and we have one of those at 4, 1. All right, so on this graph, we're going to have one local min and it is at -6 and 2. So that's our local min. And we're going to have one local maximum here. And our local max is at 3, 7. So we have a couple of false friends that we need to be careful of. So note, this point is neither a max or a min. And the reason for that is, remember, at a min, it has to go from decreasing to increasing. Well, at this point, it goes from constant to increasing, so it's not a min. So if your graph ever changes from constant to anything, or from anything to constant, it can't be a local max or a local min. It has to change from increasing to decreasing, or from decreasing to increasing. So this guy is also a neither. All right, so now let's take a look at our next example, and we're going to need our graphing device to assist. So graph the function and estimate the intervals on which the function is increasing or decreasing, and any local maxes or any local mins. So let's go ahead and grab our graphing device. So we go to our y equals, and we need to put in this function. So we have 5 minus, and to get our absolute values, we press alpha window, and we take our very first choice, which is ABS for absolute value, and then we have x minus 2. We press graph, and we get something that looks like this. So it says estimate the intervals of increasing and decreasing and find any maxes or mins. So we can use our eyeball metric, but our calculator will also help us find that point more precisely. So we're going to want to use our calculate menu. So we press second and trace to get calculate, and we're trying to find a maximum in this case. So we're going to go to choice number 4, and then our calculator is going to ask us 3 questions. We need to pick an x bound or a left bound that's to the left of the maximum. My cursor's to the left. And then it says right bound. So I have to move until I'm to the right of the maximum, press enter, and then I move back as close to the maximum as I can get where it says guess, and I press enter. And my calculator gives me this value. And everybody's calculator might give them a slightly different value because of the way it's calculated. In this case, we're going to want to do some rounding, because when our calculator says 1.9999979 and 4.9999, we're going to say that this one looks like it should be 2, and this one looks like it should be 5. And our graph changes from increasing to decreasing at that point. So our intervals of increasing are going to be from here to here, and our intervals of decreasing are going to be from that maximum here. So we have our ordered pair is 2, 5. So we're going to be increasing from negative infinity to 2, and then we are going to be decreasing from 2 to positive infinity. And since we changed from increasing to decreasing, we're going to get a local max at 2, 5. A point C, f of C is an absolute max or global max if f of C is greater than or equal to f of x for every x in the domain of f. So a point is an absolute max if it's greater than or equal to the function at every point in its domain. So for every x in the domain of f. And similarly, a point CF of C is an absolute or global min if f of C is less than or equal to f of x for every x in the domain of f. All right, so let's take a look at example number 6. So identify the absolute max and or absolute min of this function. So absolute maxes are going to be the largest y value. So our absolute maximum is going to be here. That has our largest y. And we're going to have the ordered pair, -1 and 6. So then we want to find our local, or not our local, but our absolute minimum. So that would be our smallest y. So we come looking here, but we run into a bit of trouble. So our graph has a hole here. And our hole is located at 8, -5. So there is no y value that is smaller than every other one. We'd want it to be -5, but -5 is not in the range. So we have -5 is not in range. So there is no absolute min. Because there is no y value that is smaller than every y value. All right, so let's go ahead and resolve this. So we want to identify our absolute max and our absolute min. So our largest y value for the entire graph occurs here at 3, 7. So that's our absolute max is going to be at 3, 7. Then we have our smallest y value occurs here, and it's at -6, 2. So that's going to be our absolute min. And that's at -6 and